All right, well, today we're going to look more in depth at double replacement reactions, but first I thought I would just go ahead and review all the types with you. So remember, there's 5 main types of reactions: synthesis, decomposition, combustion, single replacement, and double replacement. And synthesis or combination, that's when you had 2 different substances combined to produce a single product. That's usually going to be 2 elements combining to give you a single product. So you'll always know it's synthesis if you just have one product. Or if you only have 2 reactants that are elements, it has to be synthesis. Okay, so if the 2 reactants are elements, it's definitely synthesis. The next one is combustion. Combustion means burning. It has to be burning, not just heating. So for instance, when we burn methane or we burn propane or we burn gasoline, oxygen is the other reactant. And then CO2 and water are going to be produced if it's a hydrocarbon burning. So if it's methane that's made out of carbon and hydrogen, or oxygen, or if it is gasoline that's made out of carbon and hydrogen, or wax that's made out of carbon and hydrogen, or propane, butane, all of those are made out of carbon and hydrogen. When those are burned in oxygen, you always get CO2 and water produced. And then, of course, you get energy, which is why we have so many combustion reactions to fuel our cars, fuel our homes, our grills, and all that. Okay, but it has to say burning to be combustion. It's not just heating. The next type, decomposition, that's like the opposite of combination. You have one reactant breaking apart into other things. It could be breaking up into another compound in an element. It could be breaking up into 2 elements or 3 elements, whatever. But when you only have a single reactant, it has to be decomposition. Single replacement, that's where you have one thing by itself, and then you have a pair, a compound that's made out of normally a positive and a negatively charged ion. So there were 3 different kinds of single replacement. We had a metal replacing a metal, and for those, you need to use the single replacement activity series chart. So with this, you look to see a higher metal can replace a lower metal. Okay, so that's one type of single replacement. Also, a metal can replace hydrogen if it's within these bonds here, these boundaries. So here, these metals from lithium down to lead can replace hydrogen from acid. For this middle arrow, these metals can replace from lithium down to, I can't see, it's so small. I think that is iron, can replace hydrogen from water, and only the top 5 can replace hydrogen from liquid water. This middle one was gaseous water, steam, and then only the top 5 can replace hydrogen from liquid water because it has to be a very reactive metal in it to be able to replace hydrogen from water. So single replacement, there's the hydrogen being replaced by a metal, metal replacing metal, and then the third type is a halogen can replace a halogen. So for that, we look at the periodic table, and if it's higher on the chart, a halogen can replace a lower on the chart. Okay, so all of those we've had in the past. And here's an example here of a metal replacing hydrogen from water. When it does replace hydrogen from water, there's only one hydrogen being produced out of the water, and then the OH is combining with the metal. So you get LiOH plus H2 when you put lithium in water. Okay, that's single replacement. Double replacement is what I want to concentrate more on today. That's when you have 2 pair. So you have a plus and a minus in this compound and a plus and a minus in this compound. Mixed together, the pluses switch places. So these could be metals or they could be positively charged polyatomic ions. Most of the time they'll be metals, or it could be ammonium because ammonium is a positively charged polyatomic ion. But a plus can only replace a plus. A plus does not combine with a plus, and a minus is not combining with a minus. Okay, so in this example, we have sodium bromide, which is mixed with lead 2 nitrate, and the sodium and the lead switch places. Now, when you switch places, you have to make sure that you balance the charges in the new compound. There was only one bromine here, but when lead combined with bromine, we needed 2 because lead is +2 in this compound. And then over here, there's 2 nitrates, but when sodium combined with nitrate, you only needed 1 nitrate. You have to balance the charges on the products. Once you make your compounds, then you balance it overall. I need a 2 here and a 2 here. Okay. So our next thing, after we have written the equation, we're going to look for what's called a precipitate. In double replacement reactions, very often there's a precipitate produced. So a precipitate is a solid that forms from these 2 ions that are more attracted to each other than they are to the water. So we have to use this solubility chart to figure out which compound is the precipitate. So I'm going to go through the solubility rules with you. Okay, so you have this paper, you should have this paper, or you can print off another copy here. So the top is the activity series to use with single replacement. The bottom is the solubility rules to use with double replacement. Okay, so from this paper here, I'm going to just kind of go through it with you. So first of all, it says soluble compounds. Okay, so soluble compounds are compounds containing the alkali metals, lithium, sodium, potassium, and so on. Okay, so those are always soluble. And then, so small. Also the ammonium ion, NH4 plus, that's always soluble. So those will never be in precipitates. If the compound has an alkali metal in it or the ammonium ion, it will not make a solid. It will not make a precipitate in a double replacement reaction. Same thing for nitrates, bicarbonates, chlorates, acetates. Those are soluble. Those are not going to be in a precipitate. So when we look back at this one, we can see this one product has sodium in it, so it cannot be the precipitate. It also has nitrate in it. It cannot be the precipitate. It is soluble. Solid means it's insoluble. So S in here is for solid. AQ is aqueous. That means it dissolves in water. But anything with sodium in it is always aqueous, always soluble. So of the 2 products, this one cannot be the precipitate. Well, let's see if this one can be. So going on with the rules, it says halides, bromine as a ion, bromide, chlorine as a ion, chloride, and I minus. Those are normally soluble, and then it says exceptions, except when it's with silver, mercury, or lead. When it's with silver, mercury, or lead, it is insoluble. So silver chloride, silver bromide, silver iodide, mercury chloride, mercury bromide, mercury iodide, lead chloride, lead bromide, lead iodide. Those are all insoluble. They are the precipitate. So here in our example, we have lead bromide. It is the precipitate. So we put an S for solid. S means solid, not soluble. S means it's the precipitate. When we did that lab with the droppers in the well plate and you mix together different things and you got some solid particles, it got cloudy, that's a precipitate, solid coming out of the solution. Okay, and that's what we're looking for. So with the solubility rules, remember that alkali metals never make a precipitate. Nitrates never make a precipitate. Ammonium ion never makes a precipitate. You can use the paper But if you remember those three, that's a lot of it. Okay, so let's do another example. Let me pull one up. Right here. Okay, so for double replacement, double replacement reactions, we have lead 2 nitrate plus sodium chloride. I would recommend when you do these, write the charges of everything on top. So you can use your polyatomic ion list if you don't remember, but nitrate is -1. There's 2 of them, so that's -2 total. So that means the lead has to be +2 in this. Over here, alkali metal is +1, chlorine is -1. In double replacement reactions, those charges don't change. They're the same on the product side as the reactant side. That's not true in the other reactions, but in double replacement, the charges stay the same. So now I'm going to switch partners so that Na is going to go with the NO3. Now, just because there's 2 NO3s over here does not mean that I put 2 here. I have to balance charges. Sodium's +1, nitrate's -1. So I only need 1 of each. When I do these, I just make a habit of bringing 1 of each over and then balance the charges. I don't just bring over 2 because there was 2 on this side. Okay, so I only need 1 of each. Then my lead is going with my nitrate. Again, bring over 1 of each, and then, my lead is going with my chloride. So just bring over 1 of each, and then balance charges. So lead was +2, chlorine's -1, so I need 2 of those. So switch partners, balance charges. Now I have to balance the equation. I have 2 nitrates on the reactant side, so I need a 2 here. That gives me 2 sodiums and 2 chlorines, so I need a 2 here. Okay, so I switch partners, balance charges to get my compounds, then balance the equation, and now I have to identify my precipitate. So based on solubility rules, I know that this one is aqueous. It's soluble according to the solubility rules. But this one is my solid. It's my precipitate. I don't care if you write aqueous or not, but you definitely need to write S for solid. Okay, it's a solid precipitate. Okay, the second one, aqueous sodium carbonate. Okay, so sodium carbonate, but carbonate's -2, sodium's +1, so I need 2 sodiums mixed with strontium nitrate. But strontium's +2, nitrate's -1, so I need 2 of those. Right, so those are my reactants. Then they're going to switch partners. Na is going to go with NO3, and strontium is going to go with carbonate. So this was +1, this is -1, this is +2, this is -2. So my charges are balanced. Those are the right compounds. That's a 3. So now I need to balance it overall. I need a 2 here, and that's balanced. And then I need to, doesn't look very much like a 3. Then I need to say which one's the precipitate. Well, this is not. This is soluble. This is aqueous because it has nitrate in it, which is always soluble, and sodium is always soluble. But continuing with the chart, let's see if strontium carbonate is insoluble. So looking at the chart, I'm down to, so also with my sulfates, sulfates are always soluble unless they're with silver carbonate, calcium, strontium, barium, and lead. So lead sulfate, barium sulfate, strontium sulfate, calcium sulfate, and silver sulfate are all insoluble. Those are precipitates. Other sulfates are soluble. That's the top part of the chart. The bottom part of the chart is showing, it's a little hard to see. Hopefully you have your own chart. back. The bottom part of the chart says insoluble compounds. So carbonates, phosphates, chromates, and sulfides are usually insoluble unless they're with alkali metals or ammonium ion. So carbonates, usually insoluble, and there in my compound, I have strontium carbonate. So that is my solid. That is my precipitate because it is precipitate. It is a carbonate, and carbonates are not very soluble. Okay, finishing off the chart, hydroxides are also not very soluble. So they're usually insoluble unless they are with an alkali metal or the ammonium ion. Okay, and so you're going to be allowed to use this chart on your quiz or test, but if you remember those other rules that I told you, that ammonium, alkali metals, and nitrates are always soluble, most of the time you're going to have one of those type of products. It's either going to have alkali metal, nitrate in it, or ammonium ion. This one happened to have the same nitrate, so that one's soluble. Okay, so then I gave you the paper of a bunch of different double replacement reactions to write. Again, make sure you do this process. Balance charges as you switch the partners, then balance the equation, then figure out which is the precipitate by looking at the solubility rules.